diagnostics and application, diagnostic plots, residuals, all the types and flavors. It's the bread and butter, baby. What's your jam?
Good morning, afternoon, or evening, Bio 6611, depending on the time of day you're watching this lecture. In this one, we're going to continue looking at simple linear regression, but this time with a categorical predictor as our example. We'll first again reintroduce our motivating example, briefly note how we might have approached the problem previously with a t-test, then see how we can use simple linear regression in R again to evaluate our assumptions and also to interpret the results. We're continuing with the motivating example from our continuous predictor lecture before this, where an investigator is interested in studying endurance and they want to, in our case here, determine if there is a difference between males and females in physical endurance during exercise. We can note from our last lecture we showed that as VO2 max increased, the time it took to run a 2-mile run decreased. So now we might want to ask the question, well, is there just a difference in time overall between males and females? Again, we have the same context of 20 subjects, 10 males and 10 females, with 30 minutes of aerobic activity, 5 days a week for a 16-week exercise study, where at the end of the study we remeasured VO2 max and the time it took to complete a 2-mile run. Here's that same VO2 max data set we saw last time, but this time our scatter plots in terms of our predictor of interest here, where we see that 0 is equal to female and 1 is equal to male. And so we see, just generally speaking, it looks like males have a bit more variability in their 2-mile run time, but on average seem to have a lower 2-mile run time relative to females who have less variability. And we also have a linear fit regression between female and male on the slide scatter plot as well. So let's start by looking at the t-test again in R. Before we learned about simple linear regression, to answer the question, after 16 weeks of exercise training, do males and females differ in time required to complete a 2-mile run? We might have just conducted a 2-sample t-test. For example, on the slide here, we first see that we will read in that data set again as a CSV, but could also just make the table with the 20 observations a data frame on our own, manually. We then might conduct a t-test, and here we're going to first assume variance equals true. The reason we're introducing this one first is because this is going to directly connect to our simple linear regression example later on. But what we can see from our output here is we can focus on that p-value of 0.004879, or less than 0.05, so we reject the null hypothesis that the 2-mile runtime is equal between males and females. And further, based on our mean group 0 being females and the group 1 being males, we can note that it looks like it's about a 2-minute difference. I'm just eyeballing those values. Now we could note that we also want to evaluate instead the unequal variance assumption for a t-test based on some of the readings we've done in class. And just for the sake of completeness, we do evaluate that here, where we see the p-value is still less than 0.05 and very similar. And so if we do assume unequal variances, we still have a significant difference as our conclusion. However, there are some limitations to just using the t-test. For example, a t-test only allows us to compare the means of our two groups, which in some cases may be what we're primarily interested in, and in other cases it may not. Simple linear regression, on the other hand, will allow us to characterize the relationship between a dependent variable, for example, the time required to complete a 2-mile run, and an independent variable such as sex or VO2 max, and then determine the extent, direction, and strength of that association. So not only do we have a single p-value that says if there's a significant difference or not, but we can then describe that directionality, the strength of it, and the extent of it in the context of simple linear regression. And so with that, let's shift gears to using R to conduct the simple linear regression analysis of 2-minute mile time by sex. Before we talk about how to conduct the simple linear regression analysis with a categorical variable, let's first discuss some nuance about how we have to code or prepare that variable for analysis. One of the most popular and common ways to do this is by creating what we would call an indicator or dummy variable. They'll denote which category this variable x is trying to summarize or represent. In the case of a two-category or dichotomous classification, we may have something like our case where sex and we say 0 is equal to female and 1 is equal to male. Or maybe smoking status where we say 1's a smoker and 0's a non-smoker. Whatever 0 is, that's what we call the reference group. And it doesn't matter which category we choose as the reference as long as we get the correct interpretation. Or in other words, we have to be very aware of what is the reference and what's equal to 1, or any other value for multiple categorical variables. And we'll circle back to this to see an example of what changes if we do reverse the coding or happen to mix them up. Before actually getting to the results of our simple linear regression, it's also helpful to delve a bit into the statistical weeds for what this represents. So once we've defined that indicator variable previously, we can really just use it in our regression model like we would any other independent variable, whether it's continuous or categorical. For example, with sex, we might have something like the expected number of minutes it takes is equal to beta naught plus beta 1 times sex. Since x equals 1 for males, we could further write this out in the form of conditional expectations, where the expected value of our outcome y given x equals 0 is equal to the expected value of the number of minutes it takes to run a 2-mile run given you're a female. What this really means then is that in our equation, we're going to plug in a value of 0 for sex, and all we're really left with is beta naught. Likewise, for the expected value of y given x equals 1, or the expected value of how long it takes to run the 2-mile run, given you're a male, we're going to plug in a value of 1 for x. And so we're now left with beta naught plus beta 1. This means that the intercept, beta naught, in our model here represents the mean response for the reference group. So essentially, whenever x equals 0, it's what's left over there. The slope beta 1 then will be the difference in the response between the two groups, or written out mathematically, the expected value of y given x equals 1 minus the expected value of y given x equals 0 will just be equal to beta 1 as the only leftover term. What we'll see in a few slides is that this approach to specifying an indicator variable will have an identical conclusion and result to the two-sample t-test that we had previously with equal variances. Okay, so now let's work through an actual example of this calculation in R. Again, we'll just briefly highlight here, this first line is fitting our model with our outcome of minutes and our predictor of male as a 1-0 indicator variable. The rest of the code below here is to generate the diagnostic plots that we're going to walk through on the following slide. So here we see our 4 diagnostic plots that may be of use. And it is a little strange to interpret these in the context of a categorical predictor because obviously it creates this dichotomous relationship where we have males are equal to 1 and females are equal to 0. What we can notice though is some of the things we've discussed previously with the scatter plot and the residual plot here at the top. There does appear to be a little more variability in males, but it may be due to this outlier observation. Otherwise, they look somewhat similar, especially with respect to their residuals. The histogram of our jackknife residuals below, again, is somewhat hard to interpret considering we only have 20 observations, but it seems to be roughly centered around 0 and does have few outliers or just one point that falls outside of that -2 to 2 range, which we might expect out of 20 observations to have 95% be between -2 to 2 and then one of those observations may fall outside that boundary. Fortunately though, looking at our PP plot, or that normal probability plot, we see that the points generally follow along the diagonal line fairly well, and so we're probably pretty safe to make our assumption of normality. With that then in mind, let's look at the actual estimated coefficients from our model. So much like we did before, we can take these estimates and plug them into our fitted regression equation where y hat will equal an intercept of 16.046 plus -2.045 for our slope times being a male. A few things to note here. 16.046 is that estimated 2-minute time or 2-mile time for females, and beta 1 is that difference for males relative to females. We can also note as well that the absolute value of t here equals 3.2077, and the p-value we have matches the earlier t-test output that assumed equal variances. So with all that in mind, let's walk through the complete interpretation of our slope parameter, or in other words, the effect of sex in our model. The first thing again in our complete interpretation is to actually look at and interpret that point estimate, which on the previous slide, beta hat 1 was equal to negative 2.045. What this means is that on average, the time required to complete a 2-mile run is 2.045 minutes shorter for males compared to females. However, again, this may not be as meaningful without an estimate of the interval to say how variable the data was around this point estimate. From the table we saw a few slides ago, the standard error for beta 1 hat was 0.6375. For our problem, again, we can use that critical value of our t-distribution with n minus p minus 1 degrees of freedom, and we see we get 2.1009, which we can then plug in here to our point estimate plus or minus that critical value times the standard error, which gets us our interval estimate that we are 95% confident that the time required to complete a 2-mile run is between 0.706 and 3.384 minutes shorter for males compared to females. One thing to note here is that besides the fact we could take the coefficients from the table and calculate this by hand, we actually have some functions in R that will do this for us. One area, though, to be aware of, or a distinction of the results, is if we use the confident function for GLM versus LM, we'll see slightly different results. So what we have on the results or output below here is that the GLM corresponding estimates from using confidence function. On the right-hand side, we see the estimates for the LM function to fit our linear regression model. What we can note is that our estimate here of our confidence interval matches the linear regression model fit with LM. The reason for this is because LM does still assume that t-distribution that we used above based on our distributional assumptions, whereas GLM is cutting to the chase and just assuming a normal distribution and using essentially 1.96 has our 95% critical value there, which does in small sample sizes like we have here with only 20 lead to some pretty different estimates of those intervals. So just something to be aware of as you're using these functions moving forward. The next thing we want to do is to make a decision based on the data we've accumulated and that evidence to determine if there might be a significant difference or association. So based on just the immediate output without having to do any extra calculations, we can just evaluate that t-statistic and its accompanying p-value to see if the slope is equal to 0 or not. In this case, we can see the calculation for t, how they get the negative 3.21 is taking that ratio or dividing beta 1 hat by its standard error estimate. And we see then that's distributed as a t-distribution with 18 degrees of freedom, which would correspond to a p-value of 0.0049. In other words, a true difference of 0 would not be consistent with our observed difference, since our t-statistic is smaller than our critical value. We thus reject the null hypothesis and conclude that the slope is not 0. Additionally, instead of trying to compare the fact that t equals negative 3.21 is less than negative 2.1009 of our critical value for our t-distribution, we could just note that the p-value is less than 0.05, and therefore we reject the null hypothesis and conclude the slope is not equal to 0. The final step before we tie everything together is to provide some measure of uncertainty. And again, here it's going to be the p-value we saw on the previous slide of 0.0049. Specifically, its interpretation is that if the null hypothesis actually was true and there was no association between sex and the time required to complete a 2-mile run, then the probability that we would observe a difference of 2.045 minutes or something more extreme is 0.0049. So again, pretty unlikely if the null hypothesis was true. The final step then is to put all 4 of those components together into this brief but concise and complete summary. And here we might say something along the lines of, there is a significant difference in the average time required to complete a 2-mile run for males versus females. On average, the time required to complete a 2-mile run is 2.05 minutes, or a 95% confidence interval around that of 0.71 to 3.38 minutes, shorter for males compared to females. Another question we may wish to describe is the amount of variation explained by sex in that association of time it takes to run the 2-minute mile. Here it actually is easier or more direct to fit with the LM function, our regression, and look at the summary because it provides that coefficient of determination summary in its output automatically, which the GLM function does not apply. Here, if we do this, we can interpret it as 36.37% of the variation in 2-mile runtime can be explained by sex alone. So if we think back to the previous lecture with VO2 max, it's obviously less of the variation, and potentially this could motivate future questions that might look at more than one variable and the interactions or relationships between multiple predictors. Before we close, let's circle back to that question about what happens if I reverse my coding for my indicator variable. For example, we've defined male to be equal to 1 and female to be equal to 0. But what if we flipped those around? So here we see a little snippet of code where we've now defined a new variable where female equals 1 and male will equal 0. We're then fitting and extracting the coefficient table for our linear regression model from GLM where female is the predictor. What we see here below then is an estimate where beta naught now is the average 2-mile time for males instead of females. So on average, males will take 14.001 minutes to run 2 miles. Whereas beta 1 is going to now be the difference for females compared to males. In fact, we can actually note in this simple linear regression case, it's the exact same number, 2.045, but the sign has flipped. When male was our predictor, we had negative 2.045 to indicate that with respect to the intercept term beta naught, males were 2.045 minutes faster. In this case, because males are the reference category and females are not, we're saying that females take 2.045 minutes longer to run a 2-mile run. So therefore, noting our reference category is important for the conclusions we draw. Otherwise, we may interpret the opposite of what the actual association is and make some inappropriate conclusions. And with that, we'll end this example of categorical predictor, and in the next lecture set, we'll look at how we can address if there is a violation of some of our assumptions in the model.